Alright students, so we're looking at geometric sequences here. So if you recall, a geometric sequence is a sequence that has a common ratio between terms. So that means we're multiplying each term times a specific number to get to the next number. Normally call that common ratio R, and you can think of that like a multiplier. So just to give you an example of a couple of sequences. Here's one of them, 100, 50, 25, 12.5, where you can see in each of those cases we are multiplying by 1/2. So our common ratio R is 1/2 in that situation. Here's another sequence, 4, 12, 36, and 108. So you can see each time we are multiplying by 3. 4 times 3 is 12, 12 times 3 is 36, 36 times 3 is 108, and so on and so forth. So we're just going to kind of do a little bit of analysis here so we can arrive at a explicit formula for the geometric sequence. So for the first term, when n equals 1, then we have 4. When n equals 2, that's the second term, so that's 12. N equals 3, we have 36. N equals 4, 108. Alright, so like I said, we're going to do a little bit of analysis. We're going to think of that first term as 4 times 3 to the 0, because if you recall, 3 to the 0 is 1, so it's just 4. Continuing along that trend, the second term, the 12, we can think of that as 4 times 3 to the first. 4 times 3 is 1, or 4 times 3 is 12. And then the next term, we can think of that as 4 times 3 squared. That's 36. And then 4 times 3 to the third, and so on and so forth. So just continuing along this thought process, that 0, we could arrive at that by doing a 1 minus 1. Now you might say, why would we write it like that? And you'll see the trend here in a second. So here we ended up with a 1. We could think of that as 2 minus 1. Okay, see, 2 over there. Third term here, the exponent we could think of as 3 minus 1 to arrive at that 2. Down here we could think of this as 4 minus 1 as a way of arriving at that 3. So that being said, we notice that in each one of these, that first number in that exponent is our n value. Okay, so that should be enough to give us an idea about where we can create this explicit formula for a geometric sequence. That is, the nth term is equal to the first term. Notice that each one of these started with a 4, which was the first term, times that common ratio, 3, since we saw that was the common ratio going on here. And then with the exponent, it's going to be n minus 1. So we had n in the first position and then minus 1. If you remember when we talked about arithmetic sequences, we also talked about the recursive formula. You can create a sequence, a geometric sequence, using either the explicit or the recursive formula. The recursive formula, well, you always have to have what's called the base case. So a sub 1 is a sub 1. You have to have that one defined, or some other base case defined. And so then the nth term is equal to the n minus 1 term times that common ratio. So for instance, the 10th term is equal to the 9th term times r, or the 50th term is equal to the 49th term times that common ratio. Just an example of how we could build a sequence using the recursive formula. We'll build that same sequence we had a moment ago, so here's our starting conditions here. With the recursive formula, you have to have at least these two pieces of information. You need to have the first value, which in this case is 4, and you need to have the common ratio. So applying that formula, we'd say the first term is 4. The second term is the first term times 3. So that's the 4 times 3. You get the 12. The third term is the second term times 3. So it's always the previous term, which arrives you at 36. The fourth term is the third term times 3. So that's where you get the 108. Fifth term, 6 is equal to the fourth term times 3, and so on and so forth. All right. One more analysis here, sort of creating another formula. So I'll go ahead and extend this sequence out to the 6th term, 972. So we have 4, 12, 36, 108, 324, and 972. Geometric sequence, there we go. And let's just say that we've been given maybe the second term, which is 12, and the sixth term, which is 972. So we're going to, now you and I know what this whole entire sequence looks like and everything else like that, but we'll pretend like we don't, or we'll just sort of like do some counting and analysis here to arrive at a pretty neat formula, I think. So based on this information, we can reason that there are 1, 2, 3, 4. So 6 minus 2, there are 4 hops from A2 to A6. We could arrive at that number by just subtracting their term number. 6 minus 2 is 4, so there's going to be 4 hops. So that would mean that if I started at 12, each one of these hops is multiplying by 4. So I could do that 12 times the common ratio, which was 4. We know, 12 times r times r times r times r, and that would arrive me at the 972 value. In other words, 12 times r to the 4th is equal to 972. If we were trying to figure out what that r value was, we could divide both sides by 12, we get 81, and then take the 4th root of 81, which if you remember, anytime you're taking some number to like you're finding the root, you could actually rewrite that as the 1/4 power. If you're taking the 4th root, it's the 1/4 power. If it was the cube root, that's the 3rd root here, it's pronounced the cube root. It would be the 1/3 power. If you're taking the square root, then it would be to the 1/2 power. And of course, that's 3. So the way that we can kind of think about this is I wrote final position, but yeah, final value. Our final value is equal to our starting value. So like our 972, our final value was equal to our starting value, which was 12, times that common ratio, and then raised to an exponent, which is the number of hops that we had. So, we saw that was 12 times r to the 4th. Writing this a little more symbolically, that would be a sub n, so the nth term is equal to the mth term times r to the n minus m power here. So normally we're thinking about this where the nth term is a little bit farther to the right, and the mth term is the leftmost term, I guess. All right, that's a great formula. Just to kind of see how that worked out in this example here, a to the 6 equals a squared times 3 to the 4th. So that 972 value was equal to 12 times 3 to the 4th, which we saw that was correct. This is a great formula to write down. So I'll box that to let you know, and let's move over to some examples. So here we go. The first 3 terms of a geometric sequence are as follows: -2, 10, -50. Find the next 2 terms of the sequence and give exact values, not decimal approximations. Well, that's not going to be difficult here. We can see that this is being multiplied by -5. That is also being multiplied by -5. So we take that -50 and multiply it by -5, and we get a positive 250. Take that 250 and multiply it by a -5, and we get a negative 1250. That's it. That's how you solve that problem. Let's go on to something a little more interesting. Here we go. This says find the 11th term of this geometric sequence. Okay, well, I've got the first term, so a sub 1, and I've got the common ratio, just kind of looking through this, 3 to 12, that's multiplied by 4. If you were in any doubt, you could just check it again. 12 times what equals 48. Take that term, divide it by this term, and you can see what your common ratio is. So now we'll apply that formula for the explicit, that is the explicit formula for the nth term. So the nth term is equal to the first term times common ratio raised to the n minus 1 exponent there. So if I'm looking for the 11th term, that's going to equal the first term, so 3, times my common ratio, 4, and then plugging in the value, 11 minus 1. So that's 3 times 4 to the 10th, which you plug that in your calculator, plug it into Desmos, you get 3,145,725. All right, that's great. Now, sometimes when you plug these numbers into the calculator, you get something that's really weird, like a scientific notation number, which does not turn into a fraction real nicely, and so you've got to do something like this. So let's look at this one right here. So this says find the 10th term, so I'll write n equals 10, of the geometric sequence whose common ratio is 1/3 and whose first term is 3. Now that 1/3 common ratio is kind of tipping me off that we are getting smaller each time. Each term is going to be 1/3 of the previous term. So we'll just keep that in the back of our mind. So a sub 1 is equal to 3. All right. So I'm just going to write my formula down here. The nth term is equal to the first term times the common ratio to the n minus 1 power. So if I'm looking for the 10th term, then that's going to be 3 times 1/3 to the 10 minus 1. So that's 3 times 1/3 to the 9. Now that would be great, except that if you type in 1/3 to the 9th, you're going to get like 5.0805 blah 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 times e to the negative 5th or something like that, and you're like, okay, that's no big deal, I'll just do a math enter and you get the same exact thing. It's 5.080526 times 10 to the negative 5th. But they're going to want your answer as a fraction, so we have to be smarter than our calculator here. And yeah, type in the calculator. It's not going to give you the right answer. There might be other tools on the web and stuff like that that you might be able to find that'll give you a good answer, but I'm going to show you something that's going to work really quick. So first thing I'm going to do is I'm going to realize that if I have 1/3 to the 9th, then I can take that 1 to the 9th and the 3 to the 9th. So 1 to the 9th over 3 to the 9th. 1 to the 9th is obviously 1, so that's not going to be a big deal. But with my 3 to the 9th, I can cancel out one of those 3's, so that I really have 3 to the 8th, because there was a 3 up there in the numerator. So here we go. 1 to the 9th is 1, and then just type into my calculator really quick, what is 3 to the 8th? Why, that is 6,561. So we've got a fraction, and it's great. We're happy about that, and this is what the official answer that your homework is going to be looking for. Okay. One more problem. Here we go. It's going to use that last formula that we talked about. So I'm going to scratch out this other guy right here. So here we go. This is a situation where we're given two terms and then they want us to find another term, but they don't give us the first term and they don't give us the common ratio, so the explicit formula one is really not going to help us out a lot here. So let's see what it says here. For a given geometric sequence, the 8th term, a sub 8, is equal to 37 over 16, and the 11th term, a sub 11, is equal to 148. Find the value of the 13th term, a sub 13. If applicable, write your answer as a fraction. All right, then we will. So kind of breaking this all up into the pieces. I'm going to kind of think of my sequence here where it comes along here, A1, A2, A3, all the way up to A8. And below that, I'm going to write 37 over 16. Then we go along A9, 10, 11, whatever. Okay, so the 11th term is 148 per the given information. And they happen to be looking for the 13th term, which I don't know what that is. That's I'm trying to figure it out. So, like I said, we always kind of have that m as our leftmost term in the n. Do you really have to have the m and the n in that order? No, but it helps and makes the formula make a little more sense, I think. So the nth, that formula that we saw just a few minutes ago was the nth term is equal to the mth term times r to the n minus m. We're going to plug in our values that we have here as a way of solving for r. So the nth term was A11. The mth term was, that's A8, that's this guy right here. And then r to the n minus m, so 11 minus 8. And so then I'll actually plug in the values. So 148 equals 37 over 16 times r to the third. So we multiply both sides by 16, divide both sides by 37, and I wrote 16 here, but we'll erase that here. So multiply both sides by 16, divide both sides by 37, so 64 equals r cubed. So the cube will take the cube root of both sides, remembering that you can write that as, or if you type that in the calculator, you can do 64 to the 1/3. So anyway, it turns out that r equals 4. Okay, great. So now I'm going to apply this formula again, but I'm going to treat this term right here, the A11, as my m and my A13 as my n. So I'll just write that formula down again. So a sub n, I don't ever seem to finish the n. Okay, so a sub 13 equals a sub m, so that would be a11 times r, which is 4, determined momentarily ago, to the 13 minus 11 power. So a sub 13 equals 148 times 4 squared, since 13 minus 11 is 2. And that turns out to be 2,368. Now, some of you might be thinking, hey, why am I even applying this formula again here? I'm at A11, and I need to get to A13. Well, right in the middle of those is A12. So from here to here is going to be, I'm going to multiply that by 4. And then from here to here, I'm going to multiply that by 4 again to end up at A13. And if you did that, that would be great. And good thing for you for thinking of that. You're still going to get 2368. Not always going to have something real nice and short there. So I want to provide the full formulaic answer that's going to work every single time. All right. So we looked at geometric sequences. We looked at the explicit formula. We looked at the recursive formula. We looked at the nth formula given an nth term. All right, and we did examples with all of those. So hope you learned something. Hope you got something useful, and good luck on your homework. Thanks for watching.